I'm going to give everyone just a few minutes to enter. While you're coming in, could you please just type your year group in the chat function, please? So again, for anyone who's coming in, if you could just put your year group in the chat, just so I have an idea of who I'm talking with today. Okay, great, thank you. So we've got a year 10. Everyone else, could you just pop your year group in the chat? Okay, year 10, year 11. I'll just give everyone else, I think, one more minute to join, and then we'll get started. Okay, everyone else, I think let's get started now. We've got a couple of year 10s, year 11s, and that's great. So obviously, welcome back to our GCSE Physics course. We're on the third week of our 4-week session. And for everyone who hasn't been here before, I'm just going to introduce myself very quickly. So my name is Darina. I study chemistry with molecular physics at Imperial College London University. And today, what we're going to be covering is electrical energy. So we're going to do a little bit of a recap on how circuits work and how to calculate electrical energy using a new equation. And then we're going to have a look at energy transfers in general. So what kind of types of energy we have. We're talking about the principle of conservation of energy, and we'll talk a little bit about efficiency. So there is some overlap in this topic with just energy in general. So I thought that I'd incorporate both the aspect of electrical energy and a bit of revision of the different types of energies that we have as well. As always, if you have a question, please do use the chat function, and I'll answer that as soon as I can. And also it'll be where we're doing our answers for the questions that we've got, because today what we have is a fairly calculation heavy topic. All right, so firstly, a little bit of revision. So from our first session together, we had a look at this equation, which was linking charge, current, and time. Now, as a little bit of revision, could anyone tell me what the units for these are? So the units for charge, that's that Q symbol. Who can remember what they are? If you can, just pop it in the chat. Go on, have a go. Can anyone remember what are the units of charge? Excellent, right. So we've got coulombs for charge, and the abbreviation for that is C. What about for current? Can anyone tell me? Begins with an A, go on. Excellent. Yes. So the abbreviation for it again is A, and it's amperes or amps. Sometimes it's abbreviated. And finally, T, well, that's just time. So what are the standard units of time that you should be using in this equation? Anyone? Just pop it in the chat. Because we're a bit specific with time, even though there are multiple units. Right, great. So seconds, well done. So time is measured in seconds, always a standard units. Okay, cool. So we've got a little bit of a practice question on this. For this one, I'm just going to give you a few minutes to just go ahead and try that. What I want us to do first is just to so look at this table of data, and this is a bit of experimental sort of technique. Can you identify an anomalous result? And just write down that time value in the chat. Which one do you think of these is an anomalous result? Any ideas? Right, great. We've got 768 as our anomalous result. Now, and just for that row then, I want you to calculate the mean and then therefore the charge of that, so the charge that flows through that battery. And remember, when we have identified an anomalous result, we don't include that in the mean. So that's, again, a bit of experimental revision for you. So whip out your calculators. It'd be great if you had an actual calculator, but if you just have your phone, that's all right as well. Remember, how do we calculate the mean? We add everything together and then divide by the number of the things that we have. And then we use the QIT triangle at the top there to work out how much charge is flowing. And once you've got an answer for that, please do get it in the chat so I can see, if it needs any more work or if people are getting that. Let's start with the mean then. Can anyone get me a value for the mean for the Durablast battery? Any ideas? Right, okay, we've got one person doing it. Okay, 800 and we've got 894, 864. I think just be careful with that addition there. So 894 is the correct answer. 864, I'm not sure whether you've included the anomalous result there. So remember, you shouldn't be including your anomalous result. All right, you read the number wrong. Yes, because the anomalous result would have actually given you 852. Fantastic, so that's the mean. And could you put it in the equation now and get me a value for the charge flowing? So remember, to use triangles, you cover up the side of the triangle that you want to find, and then you put the numbers through for the other two things. Can anyone tell me what the value of the charge flowing through that battery is? And once you're done again, just pop that number in the chat. Remember, you've got your current over here, and your time should be taken from that mean time that you've just calculated. I only want the Durablast one. Does anyone have any ideas? Come on, just pop the number through your calculator and pop it in the chat, please. Anyone? Okay, well, what you needed to do is obviously you needed to find the Q. So you're covering that up. That means that you're timesing together the current and the charge, which means that you're basically using the mean that you just calculated, which was 894, and then you're timesing it by the current flowing. So 894 times 1.25. And that is actually going to give you an answer in the thousandths. That is going to be worth, let me just click the slide. 1117.5, and that's the value with the anomaly removed. Hope everyone's got that. If anyone's got any questions, please do pop it in the chat. Right, we're not going to do the next question, but does anyone have any ideas? How would you present this data in a chart, in some kind of graphical form? What do you think would be a good idea? How would you present this data? Anyone? Well, it's categorical data, isn't it, right? So you couldn't really do it on a linear thing because we have different types of batteries that we have to put on. So probably the most adequate way of displaying the data would be in a bar chart. So at the bottom, you would just have a name of battery and the corresponding bar for the charge flowing. Right. Now, let's go back to our first topic where we thought about the work that is done, or how a circuit works, how batteries work. And we essentially said that the battery is what pushes the electrons around the circuit, right? So electrons thrown through a resistor constantly collide with metal ions and transferring energy. So we have resistors which then use up that energy. So heat is given out as the energy transfers. So that means that the battery is doing work to push the electrons around, which get pushed through resistors, and that work turns into heat energy. So we can say that the electrical work done by the battery is equal to the energy transferred to the resistor of any kind. And this means that if we can work out the energy that is produced over a certain time period or a certain voltage by a battery, it's very, very convenient to then compare it with other types of energy transfers, such as thermal, such as kinetic, if we're doing something like a motor. But firstly, we need to be able to calculate that energy, don't we? So the first equation that we've got is E, Q, and V. So this is the most fundamental way of working out the energy. E, Q, V in a little triangle. But remember that we can also remember our Q equation, and sometimes instead of Q, substitute this with IT. So Q or IT, depending on what data that you have. So for example, you could do, if you're finding the energy, you could do the equation ITV instead. And that's going to be the same as E equals Q times V. All right, again, let's have a little bit of a quick recap for units. So what are the units for energy? Can anyone have a go? Joules, excellent. What are the units for charge? Well, we've just covered them, haven't we? We've said that they were coulombs and the abbreviation was C. Finally, what are the units for potential difference? Volts, excellent, yes, and they are obviously V. Right, perfect. And well, so just remember, this is the triangle that you could use, but also keep in mind the equation that we've just done, which is that Q equals IT. Fantastic. So, yep, joules, coulombs, volts. Just as a bit of a sort of stretch question, how many joules are there in 1 kilojoule? How do we convert between them? So you've got a couple of thoughts, right? No, this lesson is not supposed to be about electromagnetism. This lesson is supposed to be about energy transfers and electric circuits. I think there might be an electromagnetism topic revision in Easter, but not during this session. So this is just me answering a comment in the chat. We've got an answer to the 1 kilojoule idea. Well done. So yes, it is 1,000. Whenever we have this prefix of 1,000, that is all, sorry, of kilo, that is always going to be 1,000. So in this case, 1 kilojoule equals 1,000 joules. Right, fab. I've got a few practice questions for working out, firstly, like coulombs again, charges, and then talking about energies and currents, same equation. I actually want to come back to this at the end of the lesson, so don't worry about this too much actually. We will be coming back. However, what I do want to do right now is these questions right here. So let's start off with just very basic. This should be taking you a very, very quick amount of time. Get your calculators out, everyone. Let's do questions 1 to 3. So remember, I hope you've jotted that equation that we have down. So that little triangle of we have E at the top, and then Q, and then V. Okay, can everyone have a go at question 1 to 3, please? And once you've got your answer, please do put it in the chat so I know when to move on. And we can talk about any mistakes. Let's have a go at the questions. We've got some questions in the chat about study resources, in particular videos. I unfortunately don't know too many video resources because I don't really use them too much during my revision. For maths, I've in the previous previous times used Khan's Academy, but I'm not sure if they do physics GCSE videos. You'd have to check that out. So has anyone got an answer for question 1? Question 1, anyone? Remember, you just use your formula. So you're covering up the E. So you're doing Q times V. You can do that in your head. You don't even need a, right? Well done, we've got an answer here. Just be careful with your units. E is in units of joules, as we just said, right? So that'd be 15 joules. Perfect. Okay, question 2. Okay, so, and question 2 is 120 joules. Well done. And for question 3, does anyone have the answer? All right, excellent. We've got 960 joules. So remember, we're just timing them together. And just a little bit in conversions again. So we've just done the first one, right? So there are 1,000 joules in a kilojoule. How many millivolts are there in a volt? Does anyone have any ideas? How many millivolts in a volt? Millivolts in a volt? Well, okay, so milli, do you guys know this from anywhere else? We know millimeter, right? How many millimeters in a meter? Well done. So someone's put 1,000 there, and that's the same thing, right? We've got 1,000 millivolts in a volt. So we're kind of just going the other way, right? So milli is a small unit. So there are 1,000 tiny little millivolts in a volt and 1,000 joules in a kilojoule, which is a big unit. So milli and kilo are kind of opposites of each other in that milli, small, kilo, big. And same thing with the millicoulombs, right? Okay, fab. I don't actually, so for this one, don't worry too much about the first 2. Let's have a go at question 6. So remember, here we're going to be have to converting units. Sorry, here we're going to have to convert units. Okay, so we've just got a question. Does centivolts and centicoulombs exist? So centi is technically a prefix that is completely fine, and obviously it just means a hundredth, right? Just like centimeters, but it's not used terribly frequently. So I don't know if you've seen, but water bottles have centiliters sometimes. So you can use that unit. Everyone will understand you. It's just not common at all. And I wouldn't see it in a question. So can anyone have a go at question 6 there? Question 6. Anyone? Remember, you have to convert the units correctly and then put it through your calculator. You should just get the correct answer off there. I hope everyone's got a calculator. If not, don't worry about the units. Treat it as a coulomb and a volt because that's a bit more difficult to do on a phone, but I still want an answer. Okay. Right, perfect. So some people are getting back. So for that last one, be careful with the way that you're converting. A millicoulomb is going to be 0.001 of a coulomb, right? Because you're dividing by 1,000. So when you're expecting an energy, you're expecting really tiny, tiny energy. Yeah. So divide by 1,000. Don't multiply when you have milli. When you have kilo, that's where you're multiplying by 1,000. So yep, well done to the people who participated. Let's have a look at then finally section C. So this one's just requiring a bit of rearrangement. Think about the triangle that we had drawn up before. Let's do question 8 and you can have another go at that unit conversion. And once you've got it, just pop it in the chat. Okay, so I've given you a bit of time to do that. So with the correct unit conversion, you would have a rearrangement of the equation. So this time you're finding the voltage, you're covering the bottom right, you do energy over charge. So you're doing 6 divided by 24 divided by 1,000. So that's exactly how I put it into my calculator. And therefore I would get 250 out of that. All right, fantastic. If we have a bit more time at the end, we might come back to these, but I think that's a bit that's enough of practice. So let's move on to energy in general. And then at the end, if you, oops, that's what I meant to do, apologies. And then at the end, if we have enough time, then we will come back to this. Right. Energy in general. Obviously, we know that energy is required to do work. We usually burn fuels to release energy. That's a kind of thermal energy. And we get most of our energy sources from Earth. Now that we've discussed electrical energy, ways of working out electrical energy, we've got the equation. I've explained, obviously in terms of work done, but work done is an energy transfer. They're essentially the same thing. Now that we explained it in terms of electricity, let's have a look at the other things that it can be transferred into as well. So energy can obviously exist in many forms, and the energy can switch between these kind of forms. The first one we have is thermal or heat energy. So obviously this is the energy of an object due to its temperature. So really, really hot means we have a lot of heat and or thermal energy. Second one is light energy. And this energy is in the form of visible, EM radiation. If you're doing waves at the moment, you should know exactly what I'm talking about. So all of these do have their own formula for working them out. We don't need to know it for every type of energy. So light, for example, we don't need to know this, but thermal energy, if we were trying to work out, for example, the temperature change caused by a particular resistance, we might use the Q equals MC delta T here. And so we'd have the change in temperature. Q is going to be the same as the energy that you're supplying, so the electrical energy. So we can equate those equations to each other. Right. Obviously, we've got electrical energy. This is energy transferred by an electric current. And I've got a question saying, you're saying, okay, are there any fossil fuels or resources on Mars or the moon, anything like this? So the fossil fuels that we have on Earth are obviously the remnants of organic compounds. So there's stuff like biomass, etc., which has over the years became fossil fuels, which we see now. It's mostly carbon and stuff, obviously, hydrogen as well. So I wouldn't expect to find fossil fuels on the moon or on Mars. So probably not, no. But the sun is obviously also present there, so solar energy would still be perfectly viable. Okay, so we've got electrical energy, we've got sound energy. So obviously this is when we have energy in the form of a sound wave. So you mentioned 4 types there, just as examples. Can anyone think of any other types of energy? So we've got thermal, light, electrical, sound, any other types of energy that anyone can think of? Any ideas? Right, okay, we've got electromagnetic energy. That one is usually called electrostatic. That is the attraction of 2 oppositely charged objects. Yes, great, that's a type of, well, you wouldn't really have it as a type of energy itself. It's a type of force. You have actually like potential energy in that case, but we don't really study that at GCSE. Okay, nuclear energy. Yes, that is perfectly fine. So nuclear energy, obviously the energy released when nuclear reaction is taking place. Light energy, yes, great. So we actually have already discussed this one, light energy. Any other ideas what kind of energy there is? What kind of types of energy? Okay, well, we've had some good suggestions there, so well done. Other types include kinetic energy. Obviously, that's when a object is moving. And we have stuff like, so again, we have equations to relate kinetic energy to potentially other types of energy and work out how much energy a moving subject has. That is Ke equals half mv squared. So that's half the mass times the velocity squared. Okay, we also then have as I think, yeah, so kinetic energy increases as the object's speed is increased. So when something is moving. Chemical energy was mentioned. So chemical energy is what we gain when we eat, for example, a piece of food like a cake or whatever, and also is the energy stored within batteries. So when we actually have an electrical circuit, the energy that's initially stored is as chemical energy, and then it gets converted into electrical energy. If you've got something plugged into the main supply, however, that is coming at you straight as electrical energy. So yeah, energy is released when chemical reactions take place. Next, as mentioned, we do have nuclear energy. So this is energy that is released when nuclear reactions take place. And this is actually, if you have gotten that far in the topic yet, nuclear fusion is how the sun burns. So this is the energy that actually is the source of the sun's energy itself. Right, next we have potential energy. Now, potential energy is typically gravitational potential energy is what we talk about when we say potential energy, but it's potential energy is just like the capacity that something has to move in a certain way, or the kind of like the stored energy that it has due to its position. And first one is GPE, and again, remember GPE equals half mgh. Sorry, just mgh. I don't know where that half came from. Equals mgh. And remember, the further away from the surface of the Earth that you get, the higher is your gravitational potential energy. So an example of an increasing gravitational potential energy is obviously something like going on a roller coaster or climbing a mountain, something like that. Gravitational potential energy very usually is converted to kinetic energy. So when you get to the top, you then accelerate downwards, getting quicker, and that is going to be GPE going into KE. Perfect. So next we have elastic potential energy, is another type of potential energy. So that is when we stretch a spring, or elastic band, anything like that. Obviously, if we keep it stretched, it's going to want to spring back, right? So that is us keeping it at a particular potential energy. And it means that when we let go, this energy that it has stored is going to make it move really quickly, spring back into shape. All right, so this is the energy stored in a stretched or squashed object. So stuff like they've got an example. So we've got an example here of a like a little sling used to, well, throw rocks, to be honest, and vandalism and stuff like that. But this has elastic potential energy. Sometimes this is also known as strain energy, but at GCSEs, usually we just call it EPE, elastic potential energy. All right, okay, well, how do we measure this energy? As we've talked about, energy is measured in joules. You remember that very well. And what is really useful to remember is that work done and energy transferred is essentially the same kind of idea. Work done is measured in joules, energy transferred is measured in joules. If I'm doing work in the physics way, right, by raising an apple up, I am therefore transferring energy to it. So doing work is an energy transfer. What kind of energy would my apple gain if I lifted it up like that? Does anyone have any ideas? What kind of energy would my apple gain? If I'm lifting it up, anyone got any ideas? So because the only thing I'm changing really is the height of the apple, this would just be gravitational potential energy, right? So I'm raising it at a constant speed. I'm not really changing anything else about the apple. So this would be me just using my chemical energy inside my body to transfer into gravitational potential energy of the apple. And again, we're just bringing back our ideas of, sorry about this. I cannot seem to switch back. There we go. Okay, so right, so I was talking about GPE. Obviously here, my chemical energy that I had is being transferred into gravitational potential energy. And again, just our units that we were talking about, we have a kilojoule and also a megajoule. Megajoule is just a step up. Here we have another batch of 3 zeros. So it's actually 1,000,000 joules is a megajoule. Right, okay, so again, this is just a little bit of a fun exercise. These are all amounts of energy required to do something. So one of them is the energy of a Mars bar. Which one do you think is the energy of a Mars bar? Any idea? A, B, or C? What do you think? Which one's the energy of a Mars bar that eating an entire Mars bar would contain? Okay, so we've got an answer of A. Who thinks A? Does anyone else think A? So A is probably reasonable, right? 4,200. You think, okay, so you mean C now. So, well, that's not a lot of energy at all. Let's have a look, actually. Let's have a look. So this is, okay, we've got A. People seem to think A is fairly reasonable. A is actually only 1 food calorie, just one. So if you've ever looked at calories on, like, I don't know, biscuits or whatever, that's 4,200 joules. So does anyone want to reconsider their answer? Okay, then C. Well, C is tiny, isn't it? If 4,200 joules is 1 food calorie, all right, then B, yes. So B is actually the energy of a Mars bar. That's a lot, right? That's 1,000,000 joules. And so it's just to give you a bit of context on what a measurement of energy actually is. So in this case, a joule is not a lot of energy at all. So just one food calorie is actually around 4,000 joules, and 1,000,000 is, so we've got some ideas for what the other two are. Is the total calorie? I think the total calorie intake for, oh god, I'm really not sure. I think it's about 4,000 calories. I'm not sure at all. Sorry. I'd have to look that up later on, and maybe you can give it a quick Google. Right. This tiny bit is actually just the energy needed to produce the syllable of 1 word. So just like or something like that. That would be a tiny fraction of a joule. So really not taking up. I mean, if we spent a lot of energy talking, the world would be a much more boring place. Right. Secondly, we've got that last one, that massive number was the energy received by the Earth from the sun in just 1 day. So I don't even know how to name that. It's an enormous, enormous number. And it just adds a bit of context. We've also got another question in the chat, again, about Mars. I can tell someone's enthusiastic. So following the previous slide, is there any resources? A hexillion. Let's count the zeros. 1, 2, 3, 4, 5, 6, 7. It might well be. I'm not too sure. So again, that's something to take home for. Okay, we've got another question. Following the previous slide, is there any resources on Mars fossil fuels to produce the electricity? Again, no fossil fuels, but we could do something like solar panels, right? Okay. Or likely no fossil fuels. Next topic that we're going to talk about today is conservation of energy. So as I mentioned, when talking about the different types of energy, obviously energy is not created or destroyed. This is a really fundamental concept. It can only be transferred from one form to the other. So what this also means is that the total energy in a system, if there are no losses outside of the system, stays constant. So let's have an example of a pendulum. When the pendulum is in this location, can anyone tell me what's happening to the GPE and what's happening to the KE? Which one is at its maximum? So actually, let me give you an example. So at this, I keep doing this. So at this end, the pendulum has maximum kinetic energy or minimum kinetic energy. What do you think? Maximum or minimum kinetic energy? Any ideas? At that position, just give your suggestions in the chat. What do you think? At that position, does that ball have maximum or minimum kinetic energy? Go on, give it a shot. What do you think? The main thing to think about it is it moving? How much is it moving by when you're considering whether something has kinetic energy? So in this case, actually, if you imagine a pendulum swinging, it wouldn't be moving at that point at all, right? It's reached its maximum value. So the kinetic energy would actually be 0 at this point, whereas the gravitational potential would be maximum. So we have maximum gravitational potential energy because it's at its highest point in the pathway, and then the kinetic energy would actually be 0 because it's not moving. Then it swings, and at its lowest point, we've now got it traveling at its maximum speed. So its kinetic energy will also be at its maximum. Then, however, the gravitational potential energy, well, it won't ever really be 0 because gravitational potential energy is all relative. We can invent 0 to be any point we want because, well, we're never going to get to the center of the Earth. And even if we did, that wouldn't be where 0 was. So we just say GP is at its minimum, kinetic energy at its maximum. And then when we get to the other side, again, same thing as on the left-hand side, the GPE is maximum, the kinetic energy is just 0, right? And it swings again and again. The important thing to note is that, as we said, with the principle of conservation of energy, the total energy, the gravitational potential plus the kinetic, remains the same, even if there are, if there are no significant resistive forces. So if we're not losing any energy to the outside via things like friction, right? Okay, so let's have a look then at situations in which we do have things wasted, things lost to the outside via stuff like resistive forces and via friction. So we can class them as sort of two broad terms. We say that useful energy is energy transferred to where it is required in the form that it is wanted. So if we need a light to light up our desk space, then light energy is going to be the useful thing that we need, and it's not going to be heat energy. But if we wanted perhaps something to warm up our hands after a cold day, we wouldn't need light energy, we'd need heat energy. So useful energy transferred to rotate is required in the form that is wanted, but other forms of energy that you might produce as a byproduct are referred to as wasted energy. So we usually have wasted energy. It's usually heat, usually spreads out into the surroundings. So as I said, usually in the form of heat energy, causing sort of the energy changing device. So whatever the conversion is, for example, if it is a battery, that would be from chemical to electrical to heat. And if it's a heater, or chemical to electrical to light, or something like that. And the heat energy, which is wasted, causes the surroundings to be warmer. And again, this is pretty much just lost, right? It's very hard to harness this type of energy and use it again. Okay, so how do we then, we probably want our devices that we're using to work well. We probably want them to have a very, very low output of such wasteful energy. So how do we find that out? Well, we have a concept called energy efficiency, and that is a direct measure of how usefully energy is converted by a device. So let's have a look. Energy, let's have a look at how we actually calculate this. So efficiency basically is just useful energy output over total energy input. So let's say that I know my lamp produces 20 joules overall. Now only 14 joules of those are going to be light energy. So I put into my calculator 14 over 20, and then I work that out either as a decimal, which would be exactly that equation, or if I wanted to put it as a percentage, I'd then times it by 100. So for example, in my 14 and 20 joules example, that would be 0.7 or 70%. So yeah, because useful energy output can never be greater than the energy input, think about your conservation of energy, and the efficiency can never be greater than 1 or 100% if you're using percentages, and that's completely fine as well. So that is really useful when we're buying things like energy efficient light bulbs. So all light bulbs have an efficiency rating on them, and energy efficient light bulbs produce more useful light energy with the same amount of input electrical energy. And we have less energy wasted as heat. So can you please have a go at this question? I'm going to give you a minute to read through. So we want to calculate the efficiency of an electric motor, which produces 48 joules of useful KE, and it's supplied with 80 joules of electrical energy, either in decimals or in percentages. It's completely up to you. Whip out your calculators and have a go. So, okay, yes, well done. It's 0.6 or 60%. And there's a little question, is there MyTutor next week? Yes, I will be running my last session. That's going to be on series and parallel circuits. All right, well done to people that tried that. So our equation's obviously just this one, and we just calculate 48 divided by 80. So the efficiency of the motor is 0.6. Let's go again, just read through this question. Let's have another go at it. So this should be really quick. So we now want to do kind of a slightly different thing, use the same equation, but now we're trying to calculate the useful light output. And well done. Yes, it is 80 joules. So if we put everything into the equation, we get efficiency, and then we rearrange to get the total energy input times by the efficiency. So we do 0.2 times 400, and that will give us an answer of 80 joules. Perfect. So we've already talked about percentage efficiency. That's just times by 100 at the end. Again, in this one, could you give it to me specifically in percent, please? Any ideas, anyone? What's the percentage efficiency of this one? Right, well done. It's 12.5% to everyone who got that. I think there might have been a bit of a calculator error there with some of you. So 12.5%, great. That is the correct answer. So we have, this is how you work it out. Percentage efficiency obviously just means that times 100. Fantastic. We're not going to do this. Don't worry about that. Okay. Then we just have some ideas on how to improve that efficiency. So can anyone think of a way of improving the efficiency of a particular device? Any ideas? Just pop them in the chat. Okay, so we might want to do something like reduce heat loss. How would you do this? That's correct, but how would we reduce heat loss? Right, some great suggestions. So stuff like insulation, stuff like reducing friction with some kind of lubricant, great. So here are some ideas. Yeah, reducing friction by using a lubricant. You could be reducing electrical resistance in electrical circuits. That would mean that your heat loss is lower for those circuits. You also could be reducing air resistance. That's less friction as well. And then finally, we could, if we're not thinking about just heat anymore, we could do stuff like reduce loss to sound by tightening loose parts of a machinery or something like that. Okay, energy flow diagrams. Is anyone, I hope you're familiar with energy flow diagrams. Essentially, that's just, we've got our device, so that could be something like a iron or a mobile phone or anything like that. But the energy input, the useful output energy, and then the wasted energy. So for an electric light bulb, how do you think we're going to label the brown, green, and the red arrow? So the input energy, what kind of input energy do we have here? Input energy, what do you think? All right, we've got an answer. Electrical energy. Yeah, great. Light bulbs have electrical energy put out. What kind of useful energy are we getting out of it? Right. So we've got an answer. The output is thermal or light. The useful output is light. The non-useful output is heat or thermal energy. Yes. And because we're not using it to warm our hands up, we're just using it to provide light, right? Okay, great. So we've got obviously electrical energy, then we've got heat energy and light energy. All right, let's try another one. A microphone. What do you think would go here? Any ideas? Okay. So well done, everyone. We actually have a couple of stages to this one. So initially, we just have sound energy being input to the microphone, right? But inside the microphone, you're right, we do produce electrical impulses, right? So our useful signal would be electrical impulses, and our wasted would be, what do you think? Thermal. Yeah, it's pretty much always thermal. I'm thinking if you aren't quite sure, I would always guess thermal. Okay, so just as you said, let's do a couple last ones. So car engine again, just very quickly. What do you think I keep doing this, apologies. Right. What do you think would happen with a car engine? Right, so it's provided with chemical, you've got kinetic energy, and then thermal is a waste. Well done, that's exactly right. So well done for identifying chemical. So chemical energy is obviously the fuel that we're burning, therefore as a chemical reaction, we're releasing energy. Then we have kinetic energy as the car is now moving. And finally, we have heat and sound energy. So thermal, again, appearing everywhere. Sound, I guess, to a small extent. Right, final one, photosynthesis, again, what kind of energy processes do we have? I want input, useful output, and waste. Anyone got any ideas? Right, so we've got some suggestions. Okay, well done. So we've got light as your input, we've got chemical energy as your stores now, and your waste energy, well, again, if you're stuck, not sure, always just put heat. So with plants, it's heat as well. What about chemical for input? Well, photosynthesis is actually, are you thinking about glucose? What do you mean when? So the energy that it actually gets is from light, right? So, you know, for the photosynthesis, obviously, we do require CO2 and water to be present, but the actual energy that's coming for the reaction to happen is from light. So it's not chemical, it is actually stored in chemical at the end, which is the glucose. CO2 and H2 are not energy stored. So we're kind of increasing the energy that's stored in molecules, right? Got a bit of a complete the table below exercise. Can we start with electric motor? What's the main output energy of an electric motor? So yeah, great. What about car brakes? What's the input energy of car brakes? Kinetic as well. Perfect. What about what kind of device do you think is going from gravitational potential as their input to kinetic as their main output? What do you think? It could be any kind of object. Any ideas? Well, it's anything that's going from height to motion, right? So it could be just a falling object. It could be a roller coaster going from the tip down. So for this, any sort of falling object will do. Candle, what's the input energy for a candle? Any ideas? What's the input energy for a candle? How is it actually getting that energy to burn? So this one is chemical. So obviously we're using the wax and the wick, burning that, the chemical combustion reaction. Finally, the generator. Well, generators they turn turbines, right? That's how they generate electricity, and therefore the input energy is kinetic, the output is electrical, generating electricity. All right. Moving on to the final thing I wanted to talk about was this idea of imperfect energy transfers. And this is Sankey diagrams. So we've got kind of energy flow diagrams, and these show us exactly what we've been talking about so far. How much of the energy that is produced is wasted and how much is actually used in a useful way. So we have our device. The way that Sankey diagrams work is you have an arrow to show your input, and this is proportional to the amount of energy you're actually putting in. And then this arrow sort of splits into two smaller arrows. We've got our waste output and the useful output in gray. And as I said, the width of the arrows is proportional to the amount of energy. So if this one was, for example, something like 100 joules, so we had 100 joules of input. If this one was, let's say, 60% of the size of the width, this one will be 60 joules, and this one will be 40 joules. So the width of the arrows actually means something. Wasted energy is always, also, by the way, denoted as going downwards. So we've got our wasted output down there. Okay, so I'm not actually going to ask you to do this, but I draw a Sankey diagram for a car efficiency 20%. How do we think about this when we start the question is we think about the input energy. So again, this should be like 100% instead of 100 joules. Draw our car, and then 80% would go to kinetic energy, right? And then 20% would be wasted downwards as heat and sound. So chemical energy, kinetic energy, heat and sound energy. So it's only 20% efficient. So that's why our kinetic energy arrow is so short. That's because it is only 20%. So this isn't a very efficient car. Whereas most of it goes into heat and sound energy. So again, when you're drawing it out, if you ever ask an exam to draw it out, you should be very careful that the kinetic energy arrow would be 1/5 the width of the chemical energy one. Right. A quick exercise before we finish off for today is to fill in the word gap. So energy is required to do. Put any answers that you have in the chat, please. What is energy required to do? Oh, so we've actually got the words to choose from here. Work, well done. Energy is measured in joules. Energy cannot be created or destroyed, but can only change. Not quite. So it can only change what? It can change into different types of energy, right? So it can only change form. So remember, you're picking from the words down at the bottom, right? Okay, kinetic energy is the energy possessed by what kind of bodies? Moving bodies, fantastic. When an object is lifted up, it gains gravitational, potential energy, and heat or thermal energy is often produced as a fantastic wasted energy form. Okay, well done, everyone. That is everything that I wanted to work on for today. So thank you all for listening. Next week, I'll be doing my last session of this series, and it will be on series and parallel circuits. So I'll be recapping some really important ideas on resistance, voltage, and current, now considering their differences in series and parallel circuits and doing some quite tricky calculation questions. Does anyone have any questions before we finish off? I'll just sit and wait here in case anyone does. Other than that, please feel free to leave. I hope to see you next week. Okay, I don't think anyone has any questions. So if that's the case, I will just finish recording then.